Hello, this is Vidhya Mallikarjunan, and this is my lab report on the magnetic fields of permanent dipoles. The purpose of this lab was to understand the relationship between the position and distance of the observation location and the magnetic field of a dipole, specifically when the observation location is on axis. The secondary purpose of this lab was to collect experimental data to compare to a computational model generalizing this relationship to other locations off-axis. The most important physics principles in this experiment was the Biot-Savart law, which describes the electric field created by a current. Derived from that law is the magnetic field equation for a permanent dipole, which we used in this lab. There's also a simplified form of this equation, which is found when the observation location is on axis, given here. The model used in this experiment assumed that the magnetic field on axis would be equal to some constant k multiplied by the distance to some power n. Since we're trying to find a relationship to distance, we are primarily concerned with finding n. From k, we can also find the magnetic moment, and a preview of the results of n and the magnetic moment can be seen on screen. The experimental setup was fairly simple. The system, the phone, was first aligned with the Earth's magnetic field so that the x value reading was 0. Then the magnet, a part of the surroundings, was brought about 10 centimeters away from the magnetic sensor location. The magnet was then moved away along the ruler until the desired x value was reached. Some general observations were that when the magnetometer is far away from the magnet, it'll measure nearly 0 in the x direction as long as it's aligned with the Earth's magnetic field. And as the magnetometer approaches the magnet, the measurement of that component increases. The data was then collected for various specific measurements and then linearized using the equation above. The trend line was plotted, and from that, we found that n was approximately -3, which is what we expected, and that the magnetic moment was approximately 6.27 times 10 to the -8th. The coding results are shown here. It's important to note that one of the perpendicular arrows can't be seen as it's directly behind the closer cyan arrow, which is just the biggest one in the front. So this result was achieved by editing the starter code, in inputting the magnitude of the magnetic moment, which we found in the experimental data, defining a function for the magnetic field using the general dipole equation, which we saw at the beginning. Several observation locations were then defined on the x, y, and z axes, and finally arrows were created to represent the magnetic field at each of these observation locations using the function we defined. The results in the code and the experiment are wildly different. There are over 6 factors of magnitude difference, which is significant. This could be due to several errors, including errors in measurement, mathematical issues in correcting for the Earth's natural y and z components, and possible issues with repeatability of the experiment. I'm not entirely sure why the values are quite so different, but I do think that the program prediction is closer to the true value than the experimental results. It's also time to discuss the what-if questions. So, what if you oriented the setup that didn't account for the magnetic north of the Earth? Ultimately, the results would be different. It would result in, incorrect readings of the x component, because the magnetic field of the Earth would also be affecting that reading. So ultimately, you would have to use a correction term in order to get the desired value. And if the angle at which you were measuring changed between attempts, then ultimately that would affect the ability to consistently measure values because that correction term would be different. What if you had 2 identical magnets and you use them end to end? Ultimately, you would have a stronger net magnetic field because the magnetic field of both magnets could be added together to produce a greater magnetic effect. However, it wouldn't be exactly double the magnetic field because the center of the magnet is now farther away from the observation location. So there will be a slightly reduced effect of the magnet that is farther away. In fact, as the length is continually doubled, the strengthening of the magnetic field should drop off, as seen in this graph, which was taken from experimental data online. Thank you so much.